Hello everyone. Today let's study the general sensation and taste. Where the so the first let's study the general sensation. Where the taste is one kind of the special sensation. So first of all, so let's study the general sensation. Actually, so we have several different receptors that can detect different sensation. We can classify those receptors to two categories. So the first category is unencapsulated receptors. So we can see here, for the unencapsulated receptors, so we have the free nerve ending of the sensory neuron. Okay, so we can see here. So this is the exteroceptor. Okay, exteroceptor or the interoceptor. That means the free nerve can be found. So the exteroceptor means so that's the receptor located in the skin. Okay, because our skin is the outermost organ, right? So the interceptor means the free nerve can be also found in the visceral organs, okay, such as the digestive organs or the body cavities, okay. We can also find this free nerve ending receptors in the muscle and the tendon. Okay, so this is called proprioceptor. Proprio means CF. Okay, so that means these receptors can detect itself tissues situation. Okay, or the sensation. So anyway, we can find this free nerve ending in the skin or in the deep organs, so in the tendon and muscles. Okay, so these free nerve endings can detect can work as the thermoreceptor. That means it can detect the warm or cold. Okay. So that means it can detect the the variation of the temperature. It can also detect the concentration variation of the chemicals. So this is also called chemoreceptors. For example, uh, they can detect the pH level. Okay, so they can detect the proton. Okay, so if the solution is acidic, so that means this solution has a high concentration of proton. Okay, so that means so the free nerve ending receptors can detect the concentration of the proton. So they can also detect the mechanic stimulus. So it also termed as mechanoreceptor. For example, they can detect the pressure. Okay, they can detect pressure, or they can also detect the pain, the heart, the pinch. Okay, so this is called a nociceptor. Nociceptor. Okay. So anyway, so the free nerve ending receptors can be found anywhere. Okay, such as in the deep organs, in the skin. Okay, in the connective tissue such as the tendon muscles, joint capsules. Okay, they can also found in the cornea. Okay, in the digestive organs, sarcoma, digestive organs, mucosa. Okay, and the glands. Okay. So the second is the modified free nerve ending. So this is also called Merck disc. Merck disc. So Merck disc is found in the skin. Okay, so that means it is the exteroceptor. Okay, so so it can be found. So their function is to detect the mechanical stimulus such as the pressure. Okay, so they can detect low frequency mechanical pressure stimulus. Okay, so that's a light pressure. So it is found. So it is found in the basal layer of the epidermis. So that means it is. So it is located in the upper layer of the skin. Okay. So the third is the hair follicle receptors. So based on this name, we can see. So this. So actually, this is the. So this is one special free nerve ending receptor. So this free nerve ending actually ramps the hair follicles. Okay, so that means it is the axonal receptor. Okay, because the hair follicle is in the skin, right? So their function is to detect the mechanical stimulus. So it is the mechanoreceptor. So for example, if we stretch our hair, so we can feel the stretching, right? So this hair follicle receptor that can detect the mechanical stimulus. So the second category is uncapsulated receptors. Uncapsulated, so that means the receptor is wrapped by certain tissues. Okay, so the first is Meissner corpuscle. Okay, Meissner corpuscle. So this is the tactile corpuscle. So this receptor is located in the skin. So this is the external receptor. Okay, external receptor. Yes, we can find these receptors in the dermal papillae of the hairless skin. Okay, so especially in the nipple, external genitalia, fingertips, sole of the feet, eyelids. Okay, so this receptor actually detects the mechanical stimulus. So this is the mechanoreceptor. So it detects the light pressure. It can sense the discriminative touch. Okay, so it can distinguish the short so the short distance of the 2 points. Okay, it can also sense the vibration of the low frequency. Okay, so it is rapidly darting. So the second is Pacinian corpuscle. Pacinian corpuscle. It is laminated corpuscle. Okay, laminated corpuscle. So we can see. So this is laminated because so we can find several circle structure in this corpuscle. Okay, so it is an external receptor. Okay, because it is in the skin. Okay, in the dermis or the hypodermis. So however, we can find this one in some tendons, ligaments, okay, or the joint capsules. Okay, so this is also, so this one can also work as proprioceptors. Okay, proprioceptors. So we can find this one in the skin. Okay, in the skin, such as the finger, sole of the feet, and external genitalia, nipples. We can also find in the tendons, ligaments. And so this capacitor also detects the mechanical stimulus. So since it is located in the deep layer of the skin, so it detects the high frequency vibration. So it is also rapidly adapting. Okay. Ruffini ending. So Ruffini ending is found in the skin and tendons or ligaments. So it is the external receptor of the proprioceptor. Okay. So Ruffini ending also detects the mechanic stimulus. So it detects the deep pressure and the stretching. Okay. So the fourth is muscle spindles. Muscle spindles is specific for the proprioceptors. So it also detects the mechanical stimulus. So it is also the mechanoreceptors. So we can find these receptors in the muscle. Okay, in the skeletal muscle. So it can once the skeletal muscle contract actually contracted, so all the skeletal muscle is stretched, so actually it can so it can cause the muscle spindle is shrinked or stretched, so the muscle spindle can detect this variation of the mechanic stimulus. So their function is to detect the movement state of the muscles. Okay, so it can send the information impulse information to the membrane, and to let the membrane know the movement status of the muscles, and then the muscle can so the brain can control and regulate the muscle contraction much better, very well. Okay. So the fifth is the Golgi tendon organ. Golgi tendon organ. Golgi tendon organ is also one type of proprioceptor. Okay, so we can find this. So we can find the. So we can find this one. So we can find this one in the tendon, because so this is Golgi tendon organ, right? So this means it is specific in the tendon. So actually, the proprioceptor is also one kind of mechanoreceptor. Okay, because the proprioceptor detects the mechanical stimulus, so it can detect the tendon stretch and tension. Okay. So the function of Golgi organs is that so once the muscle contracts, so muscle will load the force and power on tendon. Okay, so the function of the tendon organ, Golgi tendon organ, is to detect the stretching of the tendon. Okay, and then so this receptor can send the impulse information to the brain, and the brain knows how how much of the power and strength loaded on the tendon, so the brain can adjust and regulate the muscle contraction to prevent the tearing of the tendon. Okay, because if that means the tendon organ can send the information to the brain to prevent the muscle contraction. Because if we don't control the muscle contraction, if the muscle contracted too much, maybe the muscle can tear the tendon from the bone. Okay, so that will cause the injury. Okay, so actually, so this is the negative feedback pathway to protect our organs and tissues. Okay. So last one is joint kinesthetic receptor. Okay, so this is also one type of the prompt receptor, and it is also the mechanoreceptor, and so this one is also the nociceptor. So it can be found in the joint corpuscle and synovial joints. Okay, so their function is to detect the status of the joints and synovial joints. Okay, because the joints. So once we move, so once we do exercise, okay, so actually our joints will move because so when we do exercise, so our joints will have the movement. Okay, so these receptors can detect all the mechanic stimulus loaded on the joints. Okay, and so these receptors can send the impulse information to the brain, so the brain can know the position of our joints. Okay, so the brain can also know if the joints get if the joints are loaded too much force or power. Okay, so because so if the joints is loaded too much force, maybe the joints will get an injury. Okay, get an injury. Maybe the joints get a dislocation of the ligament is teared. Okay, so that can cause the pain. Okay, so actually, so these receptors can detect all the movement informations of the joints and the pain of the joints. So so it can, so if the joints are injured, so the impulse information will send to the brain, so the brain can stop the muscle contraction and stop the and let us know the pain. Okay, so we can stop the movement. So this is the protective mechanism for the joints. Okay, for example, if an athlete gets the injury of their joints, so the athlete will feel pain, and he will stop the exercise immediately. Okay, so this is the joints kinesthetic receptors function. So now let's talk about the general sensation. Okay, general sensation. So first, let's talk about the 2 points discrimination test. Okay, so for example, if we use the thin sticker to touch our skin. Okay, two sticker touch our skin. So actually, so these are 2 points. Okay, so if we make the two sticker very close. Okay, so that means we decrease the distance of the 2 points. Okay, and actually, so if the distance is very minimum, actually, so our receptors cannot receptors cannot distinguish the distance of these 2 points. Okay, so our brain may get confused and just know, so may think that just one sticker touch our skin. Okay, so this is a 2 points discrimination test. Okay. So the 2 point discriminant test actually, so this depends on the density of the receptors. For example, if in our hands, okay, our hands have many receptors. Okay, so this means our hands can detect very so our hands can detect a very short distance of the 2 points. Okay, however, in other region, for example, the arm, the trunk. Okay, so in our body trunk, actually, so there are less receptors. That means so if we use two stickers attached to our body trunk, actually, so our body trunk can only distinguish very large distance of the 2 points. Okay, so that means this depends the density of the receptors. Second is tactile location, tactile localization. Okay. So this means if we use sticker touched to our body, okay, for example, so if the sticker touched to our body chunk, so we know, so our body chunk is touched by a sticker, okay. So if this sticker touched to our arm, so we know our arm so our arm is detached, okay. So our arm is touched, okay. So this is tactile localization, okay. So the density of the touch receptors, okay. So I mentioned this for the 2 points discrimination test. Okay, so that because that means different body area has different density of the receptors. Okay, adaptation of the receptors. That means if the receptors detect the stimulus, however, once the stimulus is gone, probably the receptor, so the receptors need some time to recover its function. Okay, so that means the receptor needs some times to so needed some time to detect the next stimulus. Okay, so this is adaptation of the receptors. Referred pain. That means if we feel some pain in our body region, however, we may feel this pain in the other body region. Okay, for example, so if we have the if the patient have a heart attack, okay, heart attack, so we know heart attack is induced by the shortage of the blood supply and oxygen to the cardiac muscle. Okay, so once this happened, so the heart, so we feel the chest pain. Okay, chest pain. So the pain is in the chest. Okay, because the heart is in the chest. Okay, the heart is innervated by the parasympathetic nervous system. Okay, so we will feel the chest pain. However, many patients will also feel the left arm pain. Okay, and the and also the teeth pain. Okay, so the teeth ache. So that's because the parasympathetic nervous fibers that innervated the heart we are travel with nervous fibers that innervated the left arm and the mouth together to the brain. Okay, so once the so that means so all this body regions actually share the same brain cortex region. Okay, so if the the brain cortex detects the chest pain. However, brain cortex, because this brain cortex also innervated the left arm and the mouth. Okay, so the cortex will let us feel that we have the pain from the left arm and the mouth. Okay, so this is the definition of the referred pain. Okay. Here we can see this. Here we can see this diagram. Okay. So this is our brain. Okay. Our brain has so this vertical zigzag line. So this is called a central circus. So this is a very deep circus. Okay. So the red region is the primary motor cortex. So this cortex detects the movement. Okay, so the motor movement. Okay, so the blue region is called the primary sensory cortex. Okay, cortex. So this cortex detects the sensation of our body. So if we cut the brain frontally, so we can see. So this is the so this part is the primary motor circuits. Okay, primary motor circuits. So the motor circuits actually innervated the movement common. So this cortex innervates the motor movement hormone. So the homunculi. Okay, homunculi means so it is inverted to our body position. So we can see that means our hand is in the inferior region. Okay, however, our foot is in the superior region. Okay. So we can see. So actually, so this is the parietal cortex. Okay, parietal cortex. So we can see parietal cortex actually innervated limbs. Okay, innervated limbs. We can see our feet and hands actually. So we can see most of the parietal cortex innervate the hands and the feet. Okay, that's because our hands and feet have more receptors. Okay, so that means the hands and feet need more regions of the cortex. So need more regions of the parietal cortex for the sensation detection. Okay. However, since our trunks, arms, and legs have less receptors, so we can see the regions of the parietal cortex for those body area are very minimum. Okay. Now we can see our hand. Our hand actually is in the temporal lobe. Okay, temporal lobe. We can see our face need more regions of the lobe. Okay, of the cortex. So that's because so there are so many receptors in our face. Okay, so our face, because we have the facial expression. Okay, facial expression. So all the facial expression needs neurons to innervate. Okay, so we can see. So that's because we need more regions of the cortex for our face. Um, um, Here we can also see. So this is our tongues. Okay, tongues and swallowing. Okay, because so why so because the tongue is very small. However, the tongue actually compared to the other body region, so the tongue actually need a relative large of the region of the cortex. Okay, so that's because the tongue is very important in the speech. Okay, in the speech, because one way make the speech, so the tongue has a very important role for the speech. So that's why, so the tongue need more neurons to innervate it, to regulate. Okay, also the swollen. Okay, swollen is very important movement for our life. Okay, so the swollen has to be innervated very accurately, because if so this innervation has troubles, so we will have the so we will so the food can be so the food can be um, so the food can be so the food can be aspirated to the lungs. Okay, so now let's look at this part. Okay, this part is for the primary sensory circuits, primary sensory cortex. Okay, so this is also hormone circuitry. Okay, so we can see the face is in the inferior region. Okay, however the foot, leg, and arms are in the superior region. Okay, so we can also see the so we can also so here we also have the so we also have genital organs. Okay, genital organs. Uh, 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 so we can see the more so this is also the parietal lobe. Okay, so we can see more regions of the parietal lobe actually innervate the hands, feet, and genital organs, because so the reason for this phenomenon is that so there are more sensory receptors in the hands and feet and the genital organs. Okay, so that means these organs need more neurons neurons innovation. Okay, so that's why we can find that, so these organs take the more surface take more surface of the parietal lobes. Okay, and then so we can see we have the face here. Okay, actually so the face has a very so the face has a higher density of the sensory receptors. Okay, especially for the lip. Okay, for the lip, actually the lip is a very sensitive organ. Okay, because the lip has very high density of the sensory receptors. And then so we can see we have the tongues. The tongue also takes relative higher surface of the cortex. That's because the tongue has high density receptors, for example, for the taste. Okay, for the taste. Pharynx. Okay, pharynx. Now let's talk about the taste. Okay, so the taste is very important because we can use this function to detect uh, all the taste of the food, juice, drink. Okay, and the fruit. Okay, so that's why this is very important. Okay. So actually, so the basic so the basic structure and the functional structure for the taste is called a taste bug. Okay, taste bug. Each taste bug actually consists of three cells. Okay, so these three cells are the supporting cells. Okay, supporting cells. So the supporting cells insulated the receptor. Okay, and the basal cells. Basal cells is like the stem cells. So these cells can continue differentiating to the supporting cells and the gustatory cells. Okay, so the gustatory cells. Gustatory cells are the major cells for the tasting. Okay, so these are the tasting cells. So they have the receptors to detect the taste. Okay, so the taste cells has rapid adapting receptors. Okay, so that means once the taste cells detect a certain taste, then so they just need a few seconds to detect the other taste. Okay, so the taste cells also linked with nervous fibers and contact with saliva glands and the and the and the digestive organs with nervous fibers. So once taste bugs detect the taste, so they can directly stimulate the salivary glands secretion. Okay, they can also stimulate the digestive organs to secrete the digestive juice. Okay. Now let's look at this diagram of so this slides. Actually, the taste buds is found in the tongues. Okay, actually, in the tongues. Okay. So this is a tongue. Okay, this is tongue. Actually, we can see. So here we have this V line, V-like line. Okay, so this V-like line is called sulcus terminalis. Okay, sulcus terminalis. So the V line divides the tongues to two parts. Okay, so this is the anterior part. Okay, so this is also so the anterior part is 2/3 of this whole tongue. Okay, so this is called anterior 2/3 part. Okay, so the anterior 2/3 part. So we can see. So this part contains tons of small taste bugs. Okay, so we can see this is the swirly structure. Okay, swirly structure. So this tiny taste bug are referred as fungiform papillae. Okay, fungiform papillae. However, we can see on the V-line, okay, on the sulcus terminalis, so we have this huge taste bug. Okay, so this huge taste bug is called circumvallate papillae. Circumvallate papillae. So this is circumvallate papillae. Okay. So actually, so we can find So we can find this so we can find a few test box in the posterior 1/3 of the tongue. Okay, however there are few. Okay, actually most of the test box are in the anterior 2/3 of the tongue. Okay, where in the edge of the tongue we also have a certain type of the test box. So this is buds. Okay, so this is called foliate papillae. Okay, foliate papillae. Actually, in the 2/3 anterior 2/3 part of the tongue, so we also have some tiny we also have tons of tiny test bugs. Okay, so those are called foliform papillae. Okay, foliform papillae. However, here so this slide doesn't show this one. Okay, so this is called foliform papillae. So actually, so this is epiglottis. Okay, we can see here. Actually, the epiglottis also contain a certain type of the taste bugs. Okay. So here is palatal tonsure. So this is lingual tonsure. Okay. So now if we zoom in the circumvallate papillae, so we can see so this is the papillae. Okay, so this papillae has the taste bug. Okay, taste bug. So this is gustatory cere. Okay, gustatory cere. So this is the basal cere. Okay, basal cere. So the basal cere can continuous differentiating to the gustatory cere. Okay, so the taste bug has the hole, so this is called the taste pore. Okay, so all the chemicals that can cause the taste actually can diffuse and penetrate through this hole, and then so the chemicals can contact with gustatory ceres. Okay, so the gustatory ceres can generate the taste. Okay, so the basal testatory ceres actually link with the nervous. Okay, nervous. Linked with the cranial nerve. So this cranial once the gustatory ceres generates the impulse. Okay, impulse of the taste. So this impulse can traverse through the cranial nerve to the brain. Okay, to let brain know that so we have the taste in our mouth. Okay, so this is the taste bug. So this is the tongue. Okay, so this is the stratified squamous epithelium. Okay, so we have different tastes, right? We have so actually we have 5 basic taste sensation. Okay, so the first is sweet. Okay, sweet. Sweet is induced by the sugar. Okay, all kinds of sugar. For example, the so the monosaccharide sugar. Okay, like the glucose, fructose. Okay, or the polysaccharide. Okay, polysaccharide like the starch. Okay, starch, or the alcohol. Okay, actually alcohol is the similar chemical formula. Is so the alcohol has a very similar chemical formula with monosaccharide such as the glucose. Okay, so that's why alcohol actually can induce sweet. Okay, induce sweet, and also some kind of amino acids. Okay, for example, So in the market, we have the Diet Coke, okay, Diet Coke, or the low calorie drinks, okay. Actually, so those drinks don't contain the sugars. However, so those drinks taste sweet. So why? So those drinks without sugar can still have the sweet, okay, because those drinks contains certain amino acids, so those amino acids actually also can be tasted as sweet, okay. However, so those amino acids doesn't have the calories, okay. So that's why, so those are the diet drink, like the Diet Coke, okay. So the second is the salty, okay, salty taste can be detected by the taste bug, okay. So the salty so the taste bug actually detects the metal ions, okay, metal ions to induce the salty sensation, okay. For example, for the table salt, okay, table salt is sodium chloride, okay. When the table salt is dissolved in the water, actually, the sodium ion is released in the solution, okay. So the taste bud can detect the sodium ion and then to generate the salty sensation. So the third sensation is sour, okay, sour. So the sour actually, for example, we have the vinegar in our kitchen, okay, vinegar in our kitchen. So the vinegar actually is one type of acid, okay, acid. So the acid, so we can know the characteristics of the acid is that this solution has the high concentration of the proton, okay. Proton means the hydrogen ion, okay, proton. So actually, so the taste bud can detect the proton, okay, to generate the sour sensation, okay. And then it's the bitter, okay, bitter. So the bitter is induced by many many alkali solution, okay, all the chemicals such as quinine and nicotine, okay. So the fifth is umami, okay, umami taste, okay. Umami taste is induced by the amino acids such as glutamate, okay. That's because the so this amino acid can be detected by the taste buds, okay, and generated specific action potential to show the umami, okay. For example, so if we cook the meat, okay, if we cook the meat, or if we drink the milk, okay, so all the milk, meat and the milk actually contains high concentration of the amino acids, okay, like the glutamates. So that's why, so we all like to eat the meat, okay. So we all like eat the meat because the meat actually contains high concentration glutamate, so it can let us taste very good for the meat, okay. So the actually so there are different signaling pathways are involved in this taste sensation. For example, the G protein receptors are involved in the sweet, bitter, and umami taste sensation. Okay. However, the sodium ion influx is responsible for the salty and sour taste sensation. So all the taste buds actually are are innervated by the cranial nerve. Okay, by the cranial nerve. So we can see the anterior 2/3 parts of the tongue actually is innervated by the facial nerve. Okay, facial nerve is seventh cranial nerve. Okay, so the anterior 2/3 part of the tongue actually are responsible for the salty, sour, and sweet detection. Okay, taste sensation. So the circumvalley papillae. So this V-line taste bud actually are innervated by the glossopharyngeal nerve. Okay, glossopharyngeal nerve is the ninth cranial nerve. Okay, ninth cranial nerve. So we can see this valid papillae. Okay, foliated papillae. Foliated papillae actually is specific for the milk taste sensation. Okay, so foliated papillae is located in the edge of the tongue. Okay, so we also have some taste bud located in the epiglottis. Okay, epiglottis. So the epiglottis taste buds are innervated by the vagus nerve. Okay, vagus nerve. So this is the 10th cranial nerve. Okay. So here in this slide we can see the cranial nerve 7, facial nerve, glossopharyngeal nerve, and the vagus nerve. So they can innervate the taste buds from a different region of the tongue and the epiglottis for the taste sensation. Okay. So the action potential, so the impulse will travel to the medulla and then to the thalamus. So finally, so the impulse, so the nerves will reach to the brain cortex, reach to the reach to the gustatory cortex. Okay, to generate the taste. Okay. So the medulla, okay, signal from medulla also send through the parasympathetic innervation to the salivary glands on the stomachs. Okay, so from the medulla, so the taste sensation can also stimulate the salivary glands and the stomach secretion through the medulla. Okay, so let's see this slides. Okay, here we can see. So this is the anterior 2/3 part of the tongue. So what nerve innervated this part? Actually, this is the facial nerve 7th. Okay, so this one is the ninth cranial nerve, glossopharyngeal nerve. Okay, so this is epiglottis. Actually, it's innervated by the vagus nerve. Okay, so so all these nerves actually have their own peripheral peripheral neuron. Okay, so all these neuron actually are the ganglions. Okay, are the ganglions. In this slide, so this slide doesn't show the ganglions. Okay, ganglions. Actually, so so we can ignore the ganglions. However, so we have to know so all these three nerves have their peripheral ganglions. Okay, because all these ganglions are the location of all these three nerves neuron. Okay, and then so the neurons of these cranial nerves can send the neurons to synapse at the solitary nucleus in the medulla oblongata. Okay, so in this level, okay, so the nerves will cross cross to the so the nerve will cross to a collateral side of the brainstem. Okay, that means if so this is the left side, so this is right side actually in the medulla level. So the nerve will cross to the left side. Okay, and then continue travel upwards through the pons, and then synapse at the thalamus. Okay, so this is so here so so the nerve synapse with the ventral posterior medial nucleus. Okay, and then so the middle nucleus sends the nerve to the gustatory cortex of the brain. Okay, so this is in the insula. Okay, in the insula to generate the taste sensation. So this is nervous pathway of the gustation. Okay, so we can see in the medulla oblongata. So here, so the solitary nucleus can also send the nerves to innervate the salivary glands and the stomachs. Okay, to induce the salivary glands secretion and digestive juice secretion. Okay, that's because if we if we eat foods, okay, if we have the taste sensation, so actually we have the salivary secretion and digestive juice secretion. That's because so this is reflex circle for the salivary secretion. Okay, so this is this class. Okay, you also have this documents. So this is for the super taster. Okay, super taster. Probably you guys know. Because we all know that California is very famous for the wine production. Okay, so the California actually makes all kinds of wine. Okay, since California have so many wines actually, so the farmers of the wine production actually they need certain people who has who are very good at the tasting. Okay, we call this as the super taster. So they may have so they have ability to taste all kinds of the wines. Okay, so so the wine farmer will need all these people to taste different and to taste all kinds of wines and to grade the high quality of wines. Okay, so this is why so these people are called super taster. Okay, so this document so I put some background knowledge of the super taste from different articles, so you can see actually, so those super tastes are very sensitive to the chemicals that can cause the taste sensation. Okay, actually, so you can do these small experiments. Okay, since now we do the online teachings, we cannot do this test in our classroom. So if you guys if you guys are interested, so you can do these experiments. Okay, and then so this will help you to understand the taste sensation. Okay, so this is today's class. Okay, so I hope you guys enjoy this class. Okay, have a good day.